My name is Isaiah. I'm a PhD candidate in the Mechanical Engineering Department at the University of Akron. Recently, I stumbled across a New York Times article from October 9th, 1903, titled "Flying Machines Which Do Not Fly." The article concluded that we would be able to fly in 1 million to 10 million years, provided, of course, we can meanwhile eliminate such little embarrassments as the existing relation between weight and strength in materials. Ironically, exactly 69 days later, the Wright brothers were able to eliminate these embarrassments with spruce wood, and they flew for the first time. Even though we've come a long way from using spruce wood for aircraft structures, we still use something quite similar: composites. Composites are made by combining two materials that keep distinct identities but are stronger as a team than individually. Their high strength and low weight lead to better fuel efficiency and fewer greenhouse gas emissions, making them a sustainable solution. However, the mere discovery of a material is often not enough, but how we use them in practical applications is the most challenging question. The lack of reliable methods to join composites to metals has prevented their use in many structural applications. Even with advances in joining technology with adhesives, they still present problems, as adhesive performance changes drastically with temperature. Plus, the damage of composites is often unpredictable and difficult to detect. Without understanding how composites interact with other materials and behave in extreme environments, we leave room for potential catastrophe. This is a serious problem. Think of it like this: when we're merging onto a busy highway, which one could consider an extreme environment, there are probably multiple ways you could do it, but perhaps there is one way that is the safest. The same concept applies to composites. But what if I told you that we could find the solution by looking to a beetle that bends steel pins, a shrimp that withstands punches, and an oyster with tough skin? My research finds better ways to join composites to metal by mimicking and learning from features found in nature. How? The diabolical ironclad beetle has features that resemble puzzle pieces that it uses to hold together its shell. And by combining the damage-resistant microstructures found in the mantis shrimp and pearl oyster, we can create puzzle pieces that are very strong when interlocked, eliminating the need for adhesives. But even with these advances in composite joining, a question remains: can we actually predict their damage and prevent it? To answer this, I look to the best biological model of all: humans. The human brain consists of 86 billion neurons, which send and receive signals, allowing us to learn and remember things. Just like the human brain, I use artificial neural networks, an application of artificial intelligence. Similar to how biological models have been learning and adapting over the course of history, artificial intelligence allows me to design material structures that will learn and adapt based on their environment. So why is this important? Well, lightweight materials that improve performance are required for many systems used by the Department of Defense, and methods to predict damage are imperative for the safe deployment of composite materials. Just like the Wright brothers discovered in 1903, nature can provide solutions to some of our biggest challenges. This research establishes a framework that can be used to pioneer a new class of lightweight composite joints. This will not only help create a more sustainable future, but it will enable the US to continue to produce world-class products to protect the security of our nation. Thank you.